Okay, welcome to 3-4, talking about concavity and then something called the second derivative test. So to begin, we're going to talk about this definition for what concavity is. So just to kind of put this in context, so far you've talked about using the first derivative to determine where a function's graph is increasing or decreasing. So increasing or decreasing, that's one type of behavior that a function's graph can show. So today we're looking at concavity, which is the other aspect of the graph's shape and behavior. So we're using the calculus to help us really determine what the shape of a graph looks like. So for the definition, here we go. So for concavity, we have let f be differentiable on an open interval I. So again, we're just talking about some random interval I. The graph of f is concave upward on that interval if f prime is increasing on that interval. And we say it's concave downward on that interval if f prime is decreasing. Now, let's think about this for a second. Remember, f prime represents the slope of the tangent lines. So we're saying that a function is concave upward if the tangent lines, if their slopes increase, if their slopes are getting bigger. So, for example, maybe we have this slope, and then the next tangent line would be slightly greater. And then the next one is slightly greater and slightly greater. And you'll notice you start to get sort of this rounded upward bowl shape. And that's what concave upward is. Similarly, if the slopes of the tangent lines are decreasing, so maybe we're starting with something like this, and then now we get slightly flatter, and then slightly flatter, and slightly flatter, and now you'll notice that we have sort of this part umbrella curve, and that's concave downward. So that's what it means, and that's the definition for concavity. Now let's look at this again visually, just to kind of put it in an official way. So let's just take a look at these two little parts of graphs here. So on the left we have a picture for a function that would be concave upward. And again, let's notice that if you were to draw the tangent lines, notice that all of those tangent lines, as we move from left to right, that the slopes of those tangent lines are increasing. Therefore, f prime is increasing on that interval. What I also want you to notice is that when the function is concave upward, notice where the tangent lines lie compared to the graph itself. You'll notice that all of the tangent lines actually lie below the graph. Or you can say that the graph lies above its tangent lines. So for concave upward, we can say that the graph lies above its tangent lines. And then similarly for concave downward, again, if I were to draw these tangent lines, again, as we go from left to right, notice that those tangent line slopes are actually they are decreasing. So again, when we have a function that's concave downward, f prime, the slopes of the tangents, are decreasing. And similarly, if you look at the graph, that means that the graph actually lies below its tangent lines. Okay, but now there's one more thing to think about. Remember that since f prime is also a function, and so if we're talking about f prime increasing, then that means its derivative must be positive, based on what we just learned in the previous lesson. Again, if I know that some function is increasing, then its derivative must be positive. So far you've been learning that if f increases, then f prime is positive. Well, if the function we're talking about that's increasing, though, is already f prime, then its derivative is f double prime. So there's one more statement that we can say that relates to concavity. And that statement comes in the form of this theorem here. So the theorem says, let f be a function whose second derivative exists on an open interval I. And when we talk about the second derivative existing, that means we're going to oftentimes say that the function is twice differentiable. So you've already heard us talk a lot so far about a function being differentiable. If we say that the function is twice differentiable, now we're saying that the second derivative exists as well on that interval. Okay, so if the function is twice differentiable on some interval I, then if the second derivative is positive for all values of x in that interval, then f is concave upward on that interval. And if f double prime, the second derivative, is negative for all x in I, then f is concave downward on that interval. So again, concave upward when the second derivative is positive, because remember that means f prime must be increasing, and concave downward when f double prime is negative, because if f double prime is negative, then that means f prime is decreasing. And again, that just goes back to the definition for concavity that I had in the beginning of this lesson. So that means for concave upward and concave downward, there are three statements that you need to make sure you understand are interchangeable. So these are the statements that you need to make sure you understand are interchangeable. So here on the left side, we've got f is concave upward. That's the same as saying that f prime is increasing. So remember, that's what the definition told us. But that's also the same as saying that f double prime is positive, and that's what the theorem that we just looked at tells us. Similarly, f is concave downward is the same as saying that f prime is decreasing, which is the same as saying that f double prime is negative. Okay, so these are the statements that we can use to help us determine whether a function is concave upward or downward. Now, one of the other reasons why we talk about concavity is so we can talk about this thing called a point of inflection. So if the tangent line to a graph exists at a point where the concavity changes, so let me just back up here for just a second. If the tangent line to a graph exists, remember the tangent line exists if you have, basically if the derivative exists, or if you have a vertical tangent line. So remember, the vertical tangent line, that could be a situation where you don't have a corner point or a cusp, but you just have that vertical tangent line. The derivative would still be undefined, but you would have to make sure you understood what was going on there. Okay, so if the tangent line to a graph exists at a point where the concavity changes, then that point is called a point of inflection. Okay, so to find points of inflection, we're looking for places where the concavity changes. Now, how can you tell if the concavity changes? Well, it means that the behaviors we just talked about change. So if a function changes from concave up to concave down, then that means f prime must be changing from increasing to decreasing. But that also could mean that that means f double prime changes from positive to negative. So to find points of inflection, we can do a very similar approach to what we did for finding relative max and relative min with the first derivative, but now we're going to do it with the second derivative. Okay, so we're going to find the points of inflection, if there are any, and discuss the concavity of the function. So in other words, we're going to describe the open intervals on which this function is concave up or concave down. And again, we're also going to find any points of inflection if they exist. So now that means we have to take what we've just talked about before regarding concavity. Now, if I'm looking at the equation of a function, you can't really determine from the equation very easily whether f prime is increasing or decreasing, because that would involve comparing the actual values, and nobody's got time for that. What we can do, though, is we can look at the second derivative being positive or negative, because now that's going to resemble much more what we were doing with the first derivative and increasing and decreasing. So that means in order to determine concavity and points of inflection, we actually need to find the second derivative. Well, of course, that means first we have to find the first derivative. So f prime of x will be, so the derivative of x is 1. The derivative of 2 cosine of x becomes negative 2 sine of x. But then the second derivative, so the derivative of 1 is 0. The derivative of negative 2 sine of x becomes negative 2 cosine of x. And remember that we're only talking about on the interval from 0 to 2 pi. So now, again, just like before, we're just going to set f double prime equal to 0 or undefined. So if f double prime is equal to 0 or f double prime is undefined. So if I set negative 2 cosine of x equal to 0, dividing both sides by a negative 2, that means cosine of x just has to be 0. And on the interval from 0 to 2 pi, that will occur at pi halves and 3 pi halves. F double prime will never be undefined because this is a cosine. Okay, so just like before, now let's go ahead and make ourselves a number line. We're going to make a sign chart. Now, also remember, because we're restricting the domain to only being between 0 and 2 pi, so this number line for our sign chart actually starts at 0 and ends at 2 pi. We had no domain restrictions other than restricting the domain to the 0 to 2 pi. But we did have two critical numbers here. Well, you know what? They're not even called critical numbers for f. They are critical numbers of f prime, technically. But they were the values that made our second derivative 0. So those are going to go into our number line, of course, as well. And now, just like before, we're going to make our sign chart. I've got my two rows, but here's the difference. This time, even though the first line is still for f, now the top line is for f double prime. Okay, now remember, pi halves and 3 pi halves, those were both in our table because they made f double prime 0. And so now we're just going to choose our test value. So 0 to 2 pi halves, basically we're talking about anything in quadrant 1. And in quadrant 1, we know that cosine, remember we're looking at the second derivative here, we know that cosine is positive in quadrant 1, but then it's being multiplied by a negative 2, so that's going to make f double prime negative. Between pi halves and 3 pi halves, well, that's in either quadrant 2 or 3. And in either quadrant, cosine will be negative. And if cosine is negative, and then that gets multiplied by a negative 2, that's going to become positive. And finally, 3 pi halves to 2 pi, that's quadrant 4. We know that in quadrant 4, cosine is positive, and then that gets multiplied by the negative 2, which means that's going to be negative. Now going back to the theorem, if f double prime is negative on the interval, then we know that f is concave down. And to show concave down, I'm just going to do sort of like an umbrella. Or we have a sad cyclops. On the interval from pi halves to 3 pi halves, f double prime is positive, so that means f is concave up, and we have a happy cyclops. It's kind of like a bowl. And then once again, 3 pi halves to 2 pi, f double prime is negative, so once again we return to the sad cyclops. Okay, so now we can finally answer this question. So first of all, we can discuss the concavity. So concave down, let me change colors here. So concave down, and again, we are going to mention the open intervals. So f is concave down on the interval from 0 to pi halves, and 3 pi halves to 2 pi. Oops. And then concave up on the interval from pi halves to 3 pi halves. And then for points of inflection, POI, just to abbreviate for now, for points of inflection, again, we are looking for places where the tangent line exists. Now notice, f prime is defined everywhere, so that means the tangent line does exist for all values of x. So anywhere that f double prime changed signs, anywhere that the concavity changed, we can have a point of inflection. So we do have a point of inflection at pi halves, comma, f of pi halves, which we'll figure out in just a moment, and also at 3 pi halves, comma, f of 3 pi halves. So let's figure that out. So f of pi halves, that's going to be pi halves plus 2 times cosine of pi halves. Well, cosine of pi halves, remember, is just 0, so that term goes away, and we just get pi halves, comma, pi halves. And then for 3 pi halves, again, we're going to have 3 pi halves plus 2 times cosine of 3 pi halves. Once again, that term becomes a 0, and we just get 3 pi halves. So there are the points of inflection for this function, as well as the intervals for which this function is concave down or concave up. So again, hopefully you see it's very similar to what we did for increasing and decreasing, except now we're talking about f double prime being positive or negative, and how that's making f concave down or concave up. All right, so let's do one more example here. F of x equals x over x squared minus 4. So remember, first thing we really should be doing is looking at domain. So first of all, if I look at this function, we do have a denominator. So we know that this function f is going to be undefined when x is plus or minus 2. So our domain is that x cannot equal plus or minus 2. So we've got two domain restrictions, and just like what we did with increasing and decreasing in that sign chart, those domain restrictions will go into our sign chart. Okay, so now we need to find the second derivative of a quotient. So as you can probably imagine, this starts to get a little bit messy and a little bit time consuming. So that's one of the reasons you will not see a whole bunch of these assigned, not because you shouldn't be able to, but just because of the time involved. So let's find f prime very quickly here. Of course, you are welcome to change this into a product with a chain rule as well. You can do that. And for the sake of time, I'm actually just going to find the first and the second derivative, not in real time. I'm just going to show you the result. Okay, and just like magic, there are the first derivative and the second derivative for this particular function. Now, notice for the second derivative here, x squared plus 12 will always be positive. 2 is always positive. So when we're looking for the sign of f double prime, all we really have to pay attention to then is x, the sign of x, and the sign, positive or negative, of the denominator being cubed. Okay, so now remember, we are still looking for the zeros and undefines from the second derivative. So that means for this first, the numerator here, that's going to be 0 if x is equal to 0. The denominator will be 0 if x is equal to plus or minus 2, but remember, those were domain restrictions from the start, so we're not worrying about those so much, although they are going to end up in our table. Okay, so once again, now we're going to go ahead and set up our sign chart. Now remember, for this sign chart, we're going to include any domain restrictions and any values that made our second derivative 0 or undefined. So that means we're going to have three values here. I've got negative 2, 0, and positive 2. Oops. Let's try that again. Remember, the top line is for f double prime, the bottom line is for f. Now remember, negative 2 is in here because it made both f and f double prime undefined. 0 is in here because it made f double prime 0. Okay, so if we choose any value less than negative 2, so maybe negative 3, well, remember, in the numerator, that means x will be a negative, so I'm going to have a negative in the numerator. And in the denominator, if x is negative 3, so we're going to have negative 3 squared, which is 9, 9 minus 4, which is 5, 5 cubed is positive. So we are going to get a negative value for f double prime. Now between negative 2 and 0, we're just going to have a negative 1. So if I put in a negative 1 for x, then I'm going to have a negative in the numerator. And in the denominator, negative 1 squared is 1. 1 minus 4 is negative 3. If I cube a negative 3, that will still be negative, which means I now get a positive. Between 0 and 2, again, I'm going to have a positive now in the numerator if I'm using a 1. And in the denominator, if I'm using 1 for x, I'm going to have 1 squared, which is 1, minus 4, which is negative 3. Negative 3 cubed is going to be negative. So this is going to be negative now. And finally, greater than 2, if I use positive 3, then my numerator will be a positive. My denominator will be a positive as well, which means I get a positive. And so now, since f double prime is negative on that first interval, we know f will be concave down, sad Cyclops. From -2 to 0, f double prime is positive, so f will be concave upward, happy Cyclops. From 0 to 2, f double prime is negative, so f is going to be concave down. And finally, greater than 2, f double prime is positive, so f is concave up. So now we can finally answer the question. So concave up on the intervals, let's see, we've got -2 to 0, and from 2 to infinity, and concave down on -infinity to -2, and from 0 to 2. Now remember, we're looking for points of inflection as well, and those would be points where the first derivative, where the tangent line exists and where the concavity changes. Now remember, at -2, even though the concavity did change at -2, the function is undefined there. We actually have a vertical asymptote. So you can't have a point of inflection. There is no point there. So again, this is why it's important for us to notate in our sign chart the fact that f is undefined at this value, because that will prevent us from accidentally thinking we have a point of inflection there. So again, concavity did change, but there's not actually a point there, so not at -2. At 0, though, we do have a concavity change, and 0 was a place where our second derivative was 0. So we do have a point of inflection at the point 0, comma, f of 0, which we'll figure out in just a moment. At x equals 2, same story as at x equals -2. The function is undefined when x is 2. There is no point there, so you couldn't possibly have a point of inflection where there is no point. Now, going back to f of 0, well, f of 0, that's going to be 0 over 0 minus 4, which is just going to be 0. And that is our analysis for this function. Okay, so once again, to find concave up, concave down, and points of inflection, we are using sign charts once again, but we're using f double prime to help us determine the concavity of the function on those intervals. Okay, so everything you've seen up to this point is the primary part of the lesson. Now, I do need to cover, just for the sake of you seeing it, because there will be occasional times for us to use this, but I do need to introduce you to the second derivative test. And again, this is kind of confusing because you just saw us use the second derivative to determine concavity, but the second derivative test as a theorem is actually about relative max and relative min again, just like the first derivative test was. So here's what the second derivative test says. Let f be twice differentiable, there's that phrase again, twice differentiable on an open interval containing x equals c, such that f prime of c equals 0. Now I want you to notice right away that this is a big difference. In the first derivative test, when we were trying to find relative max or min, we were just talking about critical numbers. And remember, critical numbers were values in the domain that made the derivative 0 or undefined. And you'll notice this time we are specifically only looking at critical numbers that make the first derivative 0. So what that's telling us then is this second derivative test wouldn't even apply in a situation where maybe we have a critical number because the first derivative was undefined. So already the second derivative test is more limiting to us, which is one of the reasons why the second derivative test isn't necessarily our go-to approach. Anyway, that being said, so if you have this situation set up, if f double prime of c is negative, then f of c is a relative maximum of the function. If f double prime of c is positive, then f of c is a relative minimum of f. And here's the kicker. If f double prime of c equals 0, then this whole test fails, and we should have used the first derivative test in the first place, which is sort of offensive, right? Because here you already spent the time to find the second derivative. you could have just used the first derivative test in the first place. But again, you will see in the second half of Unit 3 where the second derivative test actually becomes fairly useful, because it's a very quick way for us to determine that we do in fact have a relative maximum or minimum in a situation where the second derivative is fairly painless to find. Okay, so this is what the second derivative test says. Now, you might be a little bit thrown off by the fact that when f double prime is negative, we have a relative maximum. And when f double prime is positive, we have a relative minimum. Normally for people that seems counterintuitive. So let me just kind of clarify that for you. Remember, if f double prime of c is negative, if f double prime in general is negative, remember that means that we've got a concave downward function. And if your function is concave downward, then remember that means your tangent lines lie above, and that means your function would have this kind of a shape, meaning you would only be able to have a maximum on that interval. Similarly, if f double prime is positive, then remember that means that your function is concave up, which means you would have to have a minimum on that interval. So that's why the second derivative seems kind of opposite of what your instinct might tell you. But it has to do with the fact that if f double prime is negative, our function is concave downward, and that's why we would have a maximum. And again, similar if f double prime is positive. Okay, so we're just going to take a look at one example using the second derivative test, just so you can see it in action, and then that is it. Okay, so we're going to use the second derivative test, if possible, to locate all relative extrema of f of x equals negative 3x to the fifth plus 5x to the third. So remember, the way this is going to work is first we need to find any critical numbers of f that make the derivative 0. So first let's find the derivative. So f prime of x equals, so using the power rule here, we're going to get negative 15x to the fourth plus 15x squared. So now if I set this equal to 0, I get negative 15x to the fourth plus 15x squared equals 0. I'm going to factor out a negative 15x squared, and that's going to leave me with just x squared minus 1, which means x is going to equal 0, x is going to equal positive 1, and x is going to equal negative 1. Okay, but now we need to find the second derivative. Not too bad since this is a polynomial. So 4 times negative 15, we're going to get negative 60x to the third plus 30x. I'm going to go ahead and factor that. So that's going to become, I'm going to factor out a negative 30x. That's going to leave me with 2x squared minus 1. So this is our second derivative here. So now remember, to locate the relative extrema, we are going to substitute our critical numbers into our second derivative and see what happens. So f double prime of 1, well, if I put in a 1, remember, we don't care about the actual value, we just care about whether it's going to be positive or negative. So f double prime of 1, so if I put in a 1 for x, I'm going to have a negative from the 30, negative 30, times a positive from the positive 1, times now 2 times 1 squared is 1, 2 times 1 is 2, 2 minus 1 is positive. So I have a negative times a positive, and that's going to be negative. So f double prime of 1 is negative, which means that at x equals 1, we're going to have a relative maximum, relative max, and this is going to be at 1 comma f of 1, which we'll come back and find, for f double prime of negative 1. Same story. If I put this in, I'm going to have a negative from the negative 30, I'm going to have a negative from the negative 1, and then 2 times negative 1 squared minus 1 is going to be positive. So negative times a positive, and that's going to become positive, which means we have a relative minimum. at -1 comma f of -1, which again we will find out in just a moment. So let's go ahead and find these in fact right now. So f of 1, if I put in 1 into our original function, that's going to be -3 plus 5, which is 2. And if I put in a -1 into the original function, that's going to be a +3 plus a -5. So 3 minus 5 is going to be -2. And then now f double prime of 0 turns out to equal 0. And again, that means the second derivative test fails, and I need to actually go back to the first derivative test. And so what that means is now I have to basically do my little mini sign chart just for f prime. Now remember, 0 is in between two other critical numbers that we found, -1 and 1. So I do have to keep that in mind when I'm choosing my test values. So between 0 and -1, that's going to be a -0.5. If I put in a -0.5 into f prime, now remember, x squared is always going to be positive. So I'm going to have a negative times a positive times, now 1/2 squared is going to be, or -1/2 squared is 1/4, minus 1 is going to be negative. So negative times a positive times a negative, that's going to be positive. And then between 0 and 1, again, 1/2, that's going to be negative from the -15 times a positive because we're squaring the x. And then 1/2 squared minus 1 again is going to be negative. So again, this is positive, which means f is increasing and increasing. So there is no change of sign. That means that f double prime, that means that x equals 0. There is neither relative maximum nor minimum. But just to make sure it's clear, just because the second derivative test fails, it doesn't necessarily mean we don't have a relative maximum or minimum there. It just means that we have to make sure using the first derivative test what's going on there. Okay, so when the second derivative test fails, it just means that it's inconclusive and that we do need to use the first derivative test anyway. Okay. So just to wrap up not only this lesson but also the previous lesson on increasing and decreasing, to put all of this together and in preparation for what tomorrow's lesson is going to bring for us, let's summarize now. So again, we've talked about if f prime is positive or negative and how that tells us whether f is increasing or decreasing. And now we've looked at if f double prime is positive or negative and how that tells us whether f is concave up or concave down. And so what that means is we actually have 4 possible shapes that we should keep in mind for parts of a graph. So those 4 possible shapes are this one, or it could be this one, it could be this one, or it could be this one. What I want you to notice is all of these are going left to right. So notice all of these, the arrow is going toward the right. So what I want you to notice for this top left shape, so this top left shape right here, notice that this is increasing because it is going upward to the right. So again, this is increasing, but it's also part of that umbrella shape. So this is also concave down. And so this shape that we have in this upper left corner, that means f prime is positive because this function is increasing, and f double prime is negative because f is concave down. For this upper right corner, now notice that this time the function is going down to the right, so this is decreasing, but it's still concave down. And that means, since this function is decreasing, that means that f prime is negative. And it also means, since this is concave down, that f double prime is also negative. Looking at this lower left corner, notice that this function is going downward to the right, so that means this function is decreasing. But now this curvature is part of that bowl shape, which means this is considered to be concave up. So if this function is decreasing, then that means we know f prime is negative. And since it's concave up, we know that f double prime must be positive. And then finally, for this last lower right corner, notice that this is going upward to the right, so this little part of the function is increasing, but it's still part of that bowl shape, so this is still concave up. And that means, since this function is increasing, it means that f prime is positive, and since it's concave up, that means f double prime is also positive. So please work really hard to make sure that these 4 situations make sense to you, because you're going to see these become a crucial part of the next lesson. All right, good luck.